Eric Burgess here, and we are given the following problem. The national average movie ticket costs $7.30. A random sample of 19 movie tickets from the suburbs of a large U.S. city indicated that the average cost was $11.30, with a standard deviation of $4.80 at the 0.01 level of significance. Can it be concluded that the national average should be more than $7.30? And then we were graciously given the steps to solve the problem. So let's go ahead and do this thing. So it says first, state the null and alternative, identify the claim. So we know we're going to have a null hypothesis, H0, and an alternative hypothesis, H1. And the first one, and well, let's look at our problem. How do we determine this? Well, we say, well, they're talking about the national average. So that's a mean. And the first one is always the mean is equal to, and the second one is determined by what they say usually near the end. So if we look at the end here, it says, can it be concluded the national average should be more than? And so they say, can it be more than? So we're saying, should it be bigger? And then more than $7.30. So they're saying it should be bigger than this amount. And at the very beginning, they say that the national average of the movie ticket is $7.30. So that is our null hypothesis and all alternative hypothesis. Now we need to identify which one's the claim, right? So this top one could be the claim or the bottom one could be the claim. Well, the claim is, what they're actually saying it should be the case. And at the end here, they say, can it be concluded? So those are key words to say, this should be the case. Can we say that this is the case? That the national average should be more than $7.30. So that makes H1 our claim. So this one is our claim. And we're done with step 1. Step number 2 is to identify the tails. So the tails are determined by the alternative hypothesis H1. And we simply need to look at the sign used here in between. So we have a greater than sign. So this indicates that it is a one-tail test. One tail. If it was not equals to, then it would be a two-tail test. And if it was less, then it would be a one-tail test. So we could tell from this sign it's a one-tail test. And we could tell that since it's greater than, that means that we're going to be going to the right. It is a right-tailed one-tail test. Because we want to go bigger, right? We want to go to this side, and that's in the direction of the right side. So that is what we would say there. Next up, we need to identify the distribution. So, right, we have T, chi, and Z distributions that we use. And so to tell this, we need to look at the standard deviation we were given. So, in the sample size too should also be considered. But in general, you can look at the standard deviation, and that usually gets you what you need to know. So it says here, random sample of 19 movie tickets from suburbs, large city, with a standard deviation of $4.80. So if we look at this, this standard deviation is tied to the random sample. So this is a sample standard deviation, right? We got the standard deviation from these 19 samples. So since it's a sample standard deviation, and also our sample size is very small, it's only 19, that means that we are going to have to use a T distribution. If this was bigger, if it was a population standard deviation, then we could use a Z-score. Or if we had an extremely large amount of samples, that could also justify using a Z-score. But some instructors run purely off the standard deviation. So go with whatever your instructor's rule is. But in this case, we know it's sample standard deviation. So we have an S of $4.80. And our N is only 19. Therefore, we're going to use a T distribution. And that's how we could justify that. And now it says step 4, use the calculator to find the test stat and the p-value. So, okay, we're told that we can use the calculator. So this is pretty convenient. So we have a mean, we have a standard deviation, and we have an N. Let me make sure I got the correct standard deviation. So $7.30 and $4.80 and 19. Cool, just double check our numbers. All right, so to do this, all we need to do is we turn your calculator on and go to stat, and then you go over to tests. And we have a t-test, so that's the one we're going to use. Now, we don't have the data. We were given the statistics directly, right? The standard deviation is a statistic. The mean is a statistic. So we're going to go to statistics, and it's going to change a bit here. And now for our mu naught is $7.30, 7.3. X bar is simply the study. We conducted a study and got a different mean, right? So our X bar from our problem, from our 19 samples, if we look up here, we had a sample of 19. We found from our 19 samples indicated that the average cost was $11.30. So we got a different number for the mean based off of our 19 samples. We got $11.30. So that's what we're going to put here. We're going to put 11.3. Our sample standard deviation came from, again, our 19 people, and that was $4.80, so 4.8. And the number of people we had, well, we had 19 people, so we put 19 in, N. And then we need to match our alternative. So we say that the mean is actually greater than. So we choose the greater than sign. And as long as you write it like this, you can just copy this symbol. So we're going to go like that. We're saying that it's greater than. And now you could choose calculate or you could choose draw. I like draw because it shows you the graph and it also gives you P a little more clearly. There's less numbers that we don't care about. So there it goes. It's drawing it for us. Beautiful. And then it gives us the P value and the T score. So from this, we get a test stat of 3.6324. And we get a p-value of 0.001. And just to show you, and we get a nice drawing. If you want, you don't have to go to draw. You can just go to just to calculate. And it will also give it to you this way. And we see we get a p-value of 9.52. And you might be saying, well, that's different. Well, it's e to the minus 4. So that's 0.000. Because we would move this over 4 times. So we go 1, 2, 3, 4. This would add 0.00952, blah, blah, blah. And if you were to round that, that would be 0.001. So using the draw will actually make p-value a little bit easier too, since it will round for you. You don't have to worry about this e to the minus 4 here. And you still get the same test stat. Exact same. So p-value is a little more accurate if you do it this way. But yeah, so you could actually here, it would be a little more appropriate for both of these if we wrote approximately. They're approximately this because these are rounded values. And so we'd say, okay, next up, it wants us to sketch in shade. So we are going to do that. So we're just going to draw a normal distribution. Like this. In the middle is 0. And then at the critical value, whatever that is, and that's determined by our alpha. So what is our alpha? Our level of significance is 0.01. So we have an alpha of 0.01. And we want to be greater than. So there's 1% of the curve here, 0.01. And we're going to shade that in. And this is where our critical value, this value corresponds to where our critical value is going to go. And we got a t-score here, but first we need to know what our critical value is. So to find the critical value, we simply do an inverse operation. So we go, normally, right, we look up, well, on the calculator, they have an inverse t. So what we're going to do is we're going to go to distribution. We're going to do a second distribution, and there's an inverse t. Since we're working with t-scores, we use the inverse t operation. Our area is right here. It's 0.01. So we put 0.01. And our degrees of freedom is going to simply be n minus 1. So our n was 19. So our degrees of freedom is 18. And we put paste. Hit enter again. It's going to think for a second. And this is our critical value. So we get a critical value of, we're going to round. I'll put the approximate. Will be extra formal. 2.55. So that means down here for the critical value. Now it's negative, but this is because I did 0.01, which is technically shaded down here. And we know that this distribution is symmetric. So I can actually just make it positive because we are on the positive side due to symmetry. So we would simply make it positive. And so we get a positive 2.55 as our critical value. Now, we can graph our test stat, right? That was 3.63 approximately. So the test stat, 3.63, lands in here. So that's in the shaded region. And that means that we are not very happy with our null hypothesis. We are very far away from it. If our null hypothesis is true, we should land somewhere here in the white region, but we didn't. We landed way out here. Also, we can look at our p-value, and our p-value is 0.001, right? That's p, and that's much less than alpha. So that means that we're going to land again in the shaded region. But I'm getting a bit ahead of myself here. Let's do step 6. So that's it. All we got to do is sketch and shade. So we sketched and shaded it. Next up, we say identify the test statistic in the critical value. So we've already got the test statistic. We found it up there. That is t is equal to 3.6324 approximately. And the critical value is equal approximately to 2.55. Now we need to decide about H naught. Since we're in the shaded region, we don't like the null hypothesis. So we would say reject the null hypothesis, reject H naught. Easy as that. And you could also say that it's because you're in the shaded region, or that that the alpha value is greater than the p-value, because the alpha value is 0.01 and our p-value is 0.001. And this is another justification. If it was less than, then we would be in the shaded region, because the p-value would be greater than this area here. And that would push us out over here somewhere into the safe area. So that's how we do step 7. Now step 8, conclude for the claim. So if we reject H naught, so meaning that we don't like this one, we don't think this one's right, that means we support this one. So we would say there is evidence. We can't say for sure that it's true just because we only did one study with 19 people. But we definitely have evidence to support the claim that, and now we have to state what the claim really was in like words. What were we saying? Well, we wanted to conclude that the national average should be more than $7.30. So we would write that here, that the national average is more than $7.30. And that's it. That's all you got to do for these kinds of problems. If you have any questions about this, let me know, subscribe, and we'll catch you in the next problem.